We've done an introduction to vectors and vector operations. Now we're moving on to section 2, which is projectile motion. Projectile motion is the two-dimensional launch of objects. This means any object that's not either dropped, so falling in a straight line, or thrown straight up, so it comes straight down. Projectile motion deals with objects that are shot at an angle and form a parabolic path. So components and vectors will be useful when we're modeling the motion of objects in the air. Vectors come into play when the objects are not launched straight up or straight down, so as I showed before, when they're launched at an angle. And these projectiles, for instance, this ball coming out of a cannon, will have two components, an x direction and a y direction, as we saw before with vectors, and they will also always follow a parabolic path. So let's look at projectile velocity for angular launch. We're looking at velocity in the x direction and the y direction because the velocity will be a vector with two components. So let's start by modeling the velocity for a projectile in a parabolic path like this one above before it lands on level ground. We're going to break the velocity for each second of flight, which I've drawn roughly on this diagram, into an x component and a y component. So let's call the x component green, and the y component will be red. Okay, so we'll start with the x component. So in this first section, we have this segment of the flight. We'll model this in the x direction, and we'll do the x direction for each segment. Again, this is just a rough drawing, so it's not completely to scale, but I'll try my best to draw the velocity components for each part of the flight. So as you can see, as the object rises and falls, the x component of velocity stays roughly the same, always the same quantity as the object keeps going in its parabolic trajectory. Now let's look at the y velocity. So once again, we'll draw the component. So y velocity starts out pretty large, but as the object approaches the top, slows down because it's decelerating on the way up due to gravity, we can see that the y velocity becomes very small until it's 0 at the top, right at this point. There is no y velocity. Now the object starts to fall. In this case, the y velocity is becoming negative because the object is approaching the ground. The object also accelerates as it goes. While the x direction of the velocity stays the same for the entire path of the projectile, the y velocity becomes increasingly smaller until 0 as it rises, and then increases once again, but in the opposite direction for the way down. Let's see how that works mathematically. So there are a few projectile velocity formulas that we should go over. These will look familiar because of vector operations that we've done in the past. So first we'll start with the x component of the velocity. As we saw from the parabola diagram, this x velocity is going to stay the same for the entire flight of the projectile. So it's always going to be the v initial in the x direction, which is v initial times cosine of theta. And as you can see in this diagram, this is a diagonal v initial. We'll have this angle theta here, and the x component of this is v initial cosine theta. That's the x velocity. Now let's look at y velocity. Y velocity is a little bit more complicated because, as we saw, the objects will accelerate and decelerate in the air due to the force of gravity. So we'll start with the same initial velocity, and we're going to use the velocity equation that we learned from chapter 2, this v final equals v initial plus at. So the v initial in the y direction will use the same object taking off at an angle, takes off from the ground. Now we're looking for the initial velocity, and now we're looking for this y direction. That's going to be v initial times the sine of the angle because it's a vertical quantity. So now we get that the final velocity of an object will be the initial y velocity, so again that's v initial sine theta minus gravity, the acceleration, times the time in flight. So those are the two equations we'll use for projectile velocity. So now we're going to do a summary of some of the main equations to model projectiles. We know from the slide before that the initial y velocity will be v initial sine theta, and the initial x velocity will be v initial cosine theta for an object taking off at an angle of theta. As the object travels up in this direction, the x velocity will stay the same, and the y velocity, as we can see, will be symmetrical to the object's path on the other side of the fall, but opposite. So the y velocity will be positive on the way up and negative on the way down. Now let's look at a way to find the maximum height, right here, of the projectile. We'll call this x top because it's the distance to the top of the projectile's path. So before we look at this equation that I have right here, let's start by deriving it. We can go back to our basic equation, v final squared equals v initial squared plus 2ax, or the distance traveled. And as you can see, this x is what we're going to be trying to find because that's the distance to the top. We know that the velocity at the top is going to be 0 because that's when the object switches from rising to falling. We don't know the v initial because there are no numbers involved here, but we'll call this v initial in the y direction because we're modeling velocity in the y direction. Squared plus 2 times g, which is the acceleration, times x. Now we can move this over to the other side. The signs will just depend on which direction you define as positive and which direction you define as negative. So actually we'll say if the object starts with a positive velocity, we'll call the acceleration due to gravity negative. Now we can see initial y velocity squared equals 2gx, divide both sides by 2g, and we come out with this equation up here. X equals v initial in the y direction squared divided by 2g. So let's look at some projectile practice problems. A ball is launched at 200 meters per second, so we'll call this v0, or v initial, at an angle theta of 53 degrees above the ground. Find the maximum height it reaches, so that's part 1, maximum height, and the total time in flight, part 2. So we'll start with the maximum height. We know from the slide before that equation for height maximum equals initial velocity in the y direction squared divided by 2g. So we can plug in our numbers here. We get that the initial velocity in the y direction is 200 sine 53 squared divided by 2, and we'll call g 10 for now to make the math easier. So 200 sine 53, I'm using the angle 53 degrees because it's roughly the angle in a 3, 4, 5 right triangle. We have 53 degrees. So this just makes the sine and cosine easier to calculate. So we'll call the sine of 53 degrees roughly 4/5. So we get 4/5 of 200. That's 160 squared divided by 20. And then we can simplify this. We get that the maximum height is 1,280 meters. That's how far the projectile reaches above the ground before falling. So now let's look at the total time in flight. We'll start with the total time to get to the top of the flight, because we know that the flight will be symmetrical, so the object will take the same time to rise as it does to fall. So the time to the top, we'll use our velocity equation. V final equals V initial plus AT. V final, if the object has reached the top of its flight and it's going to start to fall, that will be 0. V initial, that's what we got from before, 160, that's just in the y direction. A will be 10, or g, so that's negative 10 because the object is falling downwards as a result of gravity, times t, that's what we're solving for. We'll move the 160 over to the other side. 160 equals 10 times t. Divide the whole thing by 10. We get that t to the top equals 16 seconds. Now remember the last important step in this problem. We're looking for the total time in flight, not just the time to the top before the object starts falling. So in order to find the total time for a symmetrical flight, we're going to multiply this by 2. Now we get t total equals 16 times 2 equals 32 seconds. And that's the final answer. Projectile practice number 2. A man jumps from the top of one building to the top of another that is 4 meters away. So you see here this distance of 4 meters. His initial velocity is 5 meters per second, at an angle of 15 degrees above the horizontal. Will he be able to make it to the other roof if it is 2.5 meters lower than the one from which he jumps? So we'll start by breaking down his initial velocity. We know from the problem that this is 5 meters per second at an angle theta of 15 degrees above the horizontal. So in the x direction, this quantity will be 5, or the initial velocity, times cosine theta, which is 15 degrees. In the y direction, it will be 5 sine theta, so 5 sine 15 degrees. So now let's model the man's displacement. We'll use the equation displacement, or x, equals initial position plus initial velocity times time plus 1/2 acceleration time squared. We're going to do this in the y direction because that's the direction in which he's accelerating due to gravity, and that'll allow us to find his time in flight. So the initial y position, we'll call that, or the final y position, sorry, we'll call that 0. And we know that he starts 2.5 meters above his final position, so we'll say that's 2.5. His initial velocity in the y direction will be 5 sine 15 degrees times time plus 1/2 times negative 10 t squared. So now we're going to simplify this a little bit. We get, this is 2.5 t plus 5 sine 15 degrees times t minus 5t squared. So I'm actually going to plug this into my calculator, which you can't see on the side here. I'm going to put this equation, this whole thing, into my graphing tool. And that'll allow me to make a graph of the parabola of the man's flight and then solve for the 0, which will be the time at which he lands. So doing that in my calculator off to the side, I get t total for his flight equals 0.848. So now let's see how far that leads him to travel in the x direction. We know that the x velocity stays constant during flight, so the displacement in the x direction for this constant velocity, we'll call this delta x in the x direction, equals v initial in the x direction times t. So we know the t now, that's 0.848. We know the initial x velocity, that's 5 cosine 15 degrees. We multiply all of that out and we get 4.097 meters. That's how far he travels in the x direction. So if he travels 4.097 meters, the building is only 4 meters away. He can just barely make it to the other side. Projectile practice number 3. A cannon is shot on level ground, so we're treating the cannon as equal to ground level. That means the object lands at the same vertical position from which it takes off. The ball lands 40 meters away. How long was the ball in the air? So we're looking for total time. If it left the cannon at 50 meters per second at an angle of 37 degrees above the horizontal. So once again, I'm using these angles from the 3, 4, 5 triangle. This time the 3 is over here, 4, 5, and this is 37 degrees. So that'll help us to find the sine and cosine of 37 more easily. So we'll start with the initial velocity in the x direction of the object. This will be, call it v initial x, equals 50 cosine 37 degrees equals 50 times 4/5 equals 40 meters per second. This will help us to find the time in the air, because now we know that the change in x in the x direction equals v initial x times time. So this is really the range of the projectile. And we already know the range from the problem statement. It lands 40 meters away. So 40 equals 40t. Divide both sides by 40. We get that t equals 1 second. So the ball was in the air for a total time of 1 second.